Page 51, we're going to look at lesson 1.8, which is on using powers of 10 to estimate quantities. Keegan and Jeff did some research, found there are approximately this many grains of sand on Earth. I'm not sure who counted all those, but anyway, Jeff says it is about 7 times 10 to the 15th grains of sand. Keegan says it is about 7 times 10 to the 18th grains of sand. So how might Jeff have determined his estimate? How might Keegan have determined his estimate? And then which one is more logical? Well, kind of what it boils down to here is what we're looking at in this lesson a little bit, what's called scientific notation. So we have these really big numbers, or if we have really small numbers, it's hard to keep track of how big or how small they are actually. You know, after we get past millions or billions or trillions, kind of is easy to lose track of actually what the numbers are. So scientific notation, we can put them as times 10 to a number, and it's easier to compare which one's bigger, which one's smaller. So what we can do here is we can move our decimal. Our decimal would be after this last zero. Scientific notation, we have one number that's not zero and then the decimal. And this is an estimate on this problem, so it'd be after the 7. Technically, we'll get into this more in the next lesson. Normally we'd put 7.492. All the zeros at the end we don't need to put. And then we look at how many spots did we move the decimal. Well, 3, 6, 9, 12, 15, 18 spots we moved the decimal. This would be 7.492 times 10 to the 18th power. Basically, every time you multiply by 10, you move your decimal one spot to the right. So if we took this 7.492, multiplied it by 10 18 times, that'd move our decimal 18 spots to the right. We'd have to add some zeros, and then that would be our answer. This is estimated what they did, so it would be the 7 times 10 to the 18th power. And then the mistake that the person made was that they just counted how many zeros there were. They just said, oh, it's 15 zeros times 10 to the 15th, but they didn't account for the part with the 492 here, so that's why. So Keegan would be the logical answer for this problem. Example 1, Janelle is comparing the estimated populations of Japan and China. Estimated population of Japan is 126,818,019. Estimated population of China is shown. How can Janelle compare the two populations more easily? So there's China's estimated population. So what we can do to compare more easily is we can put them into scientific notation. So for China, 1,402,000,000 some odd. We could round that off. They just rounded it off to the nearest billion. So 1 billion, which is 1 times 10 to the 9th power. Our decimals here, we want it to be right after the first number that's not a 0. So that'd be 1 times 10 to the 9th power. And then for Japan, they rounded that to 100 million. 100 million, there's our decimal, and that would move 8 spots altogether. So it would be 1 times 10 to the 8th power. And then what we could look at, obviously 10 to the 9th power is greater than 10 to the 8th power. I mean, we know billions is more than millions anyway, but we could even go a step further. We could look at how many times more people are at one place than the other. And this is pretty simple with the numbers they've given us here. If we wanted to see how many times more people were at one place than the other, we would divide. In order to divide these, what we can do, we can actually split them up as two separate fractions. We can have our numbers in front as one fraction, and then we can have our 10 to whatever power as a second fraction. When you do that, you know 1 divided by 1 is 1. 10 to the 9th divided by 10 to the 8th, when you are dividing like bases, you subtract the exponents. So 9 minus 8 would be 1. So it'd be 1 times 10 to the first power, or just 1 times 10, which is 10, which means there are 10 times or we could say about 10 times as many people in China as Japan. Okay, and again, that's an estimate there, but that would be another thing we could do, might be more interesting than just saying there's more people in China than Japan. So the try it, they've changed this a little bit from what it originally was. So we have light traveling almost 300 million meters per second. Sound traveling only 332 meters per second. About how much faster is the speed of light than the speed of sound? So this explains, for example, why you see lightning first before you hear the thunder, for example. So what they did is they just rounded these off. So this is, like I said, almost 300 million. And if you look at this, there are 8 zeros in the rounded number. This would be the same as 3 times 10 to the 8th power meters per second. 322 rounded to the greatest place value is 300. There are 2 zeros, so that's the same as 3 times 10 to the 2nd power. So then speed of light's 3 times 10 to the 8th divided by 3 times 10 to the 2nd. So 3 times 10 to the 8th divided by 3 times 10 to the 2nd. If we think of splitting this up, or you can just think of the 3's canceling each other if you want, or 3 divided by 3 is 1. 10 to the 8th divided by 10 to the 2nd would be 10 to the 6th. So it would be 1 times 10 to the 6th, or just that'd be the same as 10 to the 6th. So this should just be 10 to the 6th meters per second. Or actually 10 to the 6th times faster, we could say, with what we're doing here. If we divided them, 10 to the 6th times faster. So that'd be like 1,000,000 times faster. Example 2, Matthias used a laser to measure the average thickness of human hair. A sheet of paper is about 0.0013 meters thick. How do the two thicknesses compare? So what they did, they rounded them off again to the highest place value number. So there's a 1 there after it's a 7, so we round that up to a 2, which is the same as 2 times 10 to the negative 4th power. This one we've got a small number. Small numbers are going to be to negative exponents. Remember, a negative exponent you can put in the other part of the fraction, makes it positive. So this is the same as 2 divided by 10 to the 4th power. Every time you divide by 10, you move your decimal 1 place to the left. So that'd be another way of looking at that. So that's that number in scientific notation, though. The other one, highest place value position, is the 1 here after it's a 3, so we'll just keep it a 1. So that'd be 1,000th, or 1 times 10 to the negative 3rd power. Again, we move our decimal 3 places, but we've got a small number, so it's going to have a negative exponent here because we need to divide by 10 several times to get back to that 1,000th. And so we can see then that 10 to the negative 4th, anything 10 to the negative 4th is less than something times 10 to the negative 3rd, because negative 4 is less than negative 3. So a human hair is thinner than a sheet of paper. Example 3, how is the gross domestic product, or GDP, of Canada compared to that of the United States? So they just rounded these off again. Canada 1,7 something, rounded it to a 2 with a bunch of zeros. US 17 something, They rounded it to 20 with a bunch of zeros. So Canada, it's got 15 zeros after the 2. That's 2 times 10 to the 15th. US, it's got 16 zeros after the 2. That's 2 times 10 to the 16th. So to compare, we could just say US is greater than Canada. To be more specific, we could work it out and figure out US is about 10 times greater. And again, we could figure that out by dividing these. If you divide, basically the t's could cancel, or you could write them as separate fractions, and then dividing like bases, subtract the exponents. 16 minus 15 is 1. 10 to the first power is the same as 10. So that's how we could get that. Figure out how many times greater something is than something else you get by dividing them. Then the try it tells approximately how many cars there are in the world and how many cars there are in the United States. Compare the number of cars in the world to those in the United States. So what we could do here again is just round these off. So 1 billion cars about in the world, about 200 million in the United States. So we could just go ahead and divide it at that point. Otherwise we could say this is 1 times 10 to the 9th. And this is 2 times 10 to the 8th. If we compared them with scientific notation, then we could do this. 1/2 is the same as 0.5 or 5/10. And then 10 to the 9th divided by 10 to the 8th would be 10 to the 1st. So if you have 5/10 times 10 moves your decimal over 1 spot would be 5. So what that means is 5 times as many cars in the world as in the United States. Or another way of thinking about that, the United States has about 1/5 or 20% of the world's cars, which is definitely more, per person kind of thing than what most other countries, if not all other countries, have. So key concept, just kind of recapping here, is again, if we have big numbers, we're going to have positive exponents because we have to multiply by 10 to get to that number. If you have a small number, it's going to be negative exponents because you'd have to divide by 10 to get back to that number. And again, another way of thinking about it is if you have, with our exponents, for a negative, the number is less than 1. If you have a negative exponent, so for example, if you have 4 thousandths, that'd be 4 times 10 to the negative 3rd power. Positive exponent, the number is greater than 1. So for example, if we have 300,000, that'd be 3 times 10 to the 5th power. Okay, so positive is bigger numbers, positive exponent, bigger numbers, negative exponent is smaller numbers.